Okay, so today we're going to pick it up where we left off yesterday with chapter 5. So remember, chapter 5 is our introduction to probability theory. And let's just quickly review some of the key definitions from yesterday. First, we start out with the concept of the random experiment, where we have some kind of a process taking place in such a way that all the possible outcomes of this experiment are known in advance, but the actual outcome is not known in advance. And so what we're going to want to do is calculate probabilities for these different possible outcomes. So I gave you some examples of real world experiments, although you notice they're all games of chance. There's a lot more different types of experiments that could be conducted or that might take place. But these are very good examples because it's easy to see that when you engage in these games, you know that you're essentially repeating a series of trials, we call them. And on each trial, there's a given number of outcomes. For example, with the roulette wheel, every spin has 38 equally likely possible outcomes. The numbers 1 through 36, half of which are red and half of which are black, and the 0 and 00 are green. By the way, it's not the case that with the 1 through 36, every other number is red and every other number is black. It's a little bit different than that, but half of them are red and half are black. So you may have seen roulette wheel on TV. Sometimes they pop up in James Bond movies when he's in a casino. It's a very popular game, let's just say. Choosing a card from a deck, we know that there's 52 cards, and because the cards are all of equal size and weight, choosing a card from a deck means that each card is equally likely to be chosen. So the probability of any particular card, let's say the ace of spades, is 1 out of 52. And then when you roll a pair of dice, which I'm sure you've all done at some point in your life, you know that there are 36 possible outcomes because each die has 6 faces. And so altogether, there's 36 possible outcomes. Normally, though, when we play with dice, we're not really so much interested in the individual rolls, but the sums. Okay, so if we're only focused on the sums of these dice, then the only possibilities are the numbers from 2 to 12. And they are definitely not all equally likely. As a matter of fact, it turns out that the most likely outcome when you roll a pair of dice is 7, and then the least likely outcomes are 2 and 12. Okay, now here we're going to look at a case where we're rolling a pair of dice, but we're not really focused on the individual numbers. We're only interested in whether they're even or odd. Okay, the reason we're doing this is because then the sample space is much smaller, and that will make our calculations much easier. All right, we can always have an example with all 36 outcomes, but for now, let's just focus on evens and odds. And then if that's the case, there's only 4 things that can really happen. Okay, the first roll can be either even or odd, and the second roll can be even or odd. So altogether, we can have 2 consecutive evens, even followed by odd followed by even, or odd followed by odd. Altogether, we have 4 possible outcomes, which are EE, EO, OE, and OO. And now what we're going to do is gather them up into one set. And that set has a special name in probability theory. It is often referred to as the sample space. And it's simply a set that contains all the possible outcomes of our experiment. So coming back here, for the roulette wheel, for example, the sample space would be the numbers from 1 through 36 and the 0 and 00. But anyway, once we have that sample space in place, we can define any number of events we like. Now, by the way, here in this chart, what I'm demonstrating is that each of these is equally likely to occur because we know that each individual roll is equally likely to be an even or an odd. In other words, the probability of a single die being odd is 3 out of 6 or 1/2. The probability of a single die being even is 3 out of 6 or 1 out of 2. So the probability of getting 2 consecutive evens can be obtained by multiplying the probability of a single even by the probability of another single even, or 1/2 times a half equals a quarter. So based on the same logic, all 4 possible outcomes each has the same possible, same probability, which is 1/4. Now, an event. Now, most of the time, what we're really interested in doing is calculating the probability of an event of some kind. So an event is formally defined as a subset of the sample space. In other words, the event is a set itself. It contains elements from the sample space. All of the elements in the event are also elements in the sample space. So here, F is defined as at most one even number turns up, which is the same thing as saying everything except two evens. So that means that all of these outcomes are listed here. The only one that we left out is EE, because that is where we have two evens. Okay, with F, we only have 0 evens or 1 even. So clearly, F is a subset of the sample space because every element in F is also an element of S. By the way, I just wanted to point out that if you had another set, let's say you define the set G to be 3 evens turn up, that would not be considered an event in this case because it's not possible to have 3 even numbers when you only roll the die twice. So events are restricted to being subsets of the sample space. The probability of getting 3 evens, for example, would simply be 0. Okay, but for here, if you recall, we just got through showing that each of these outcomes is equally likely and has a probability of 1/4. So how do we figure out the probability of F? Well, we can add up the probabilities of the individual outcomes, and we end up with 3/4. It's that simple. All right, just add them up. And in a case when all of the outcomes are equally likely, we can even simplify it further. All you have to do is count up how many elements there are in F and divide by the number of elements in the entire sample space. That would give us 3 out of 4 as well. Okay, so the key detail here, though, is that this is only true, what we did here, when all possible outcomes are equally likely. All right, this process of just simply counting up the number of outcomes in F divided by S, what we did here is always correct. This will always give you the correct value. And in fact, we have an example coming up where the elements in the sample space are not equally likely, and we'll see how we handle that case. Okay, so by the way, you see this notation used sometimes. This symbol, which now everybody calls it a hashtag, is actually the numbers or pound sign. That's the correct name of this. I don't know how it got to be known as a hashtag, what that's all about, but this is correctly known as a pound sign. And it was always used to represent a number, the number of, let's say, number elements or something like that would be in English the number of elements. So this formula just says for any given event E, where all the outcomes are equally likely, only when they're all equally likely, you're just counting up the number of elements in E. And then you also down here have the number of elements in S. You know, talking about this pound sign, this symbol, which has now been co-opted to represent or be used with email addresses, this one was always just simply at. Okay, at. So those two symbols were chosen at random, I think, to represent two very important ideas that we use today for very different purposes. But anyway, how about the case where outcomes are not equally likely? All right, let's try this one. Now we have a separate, when playing with dice that are not standard dice, we're playing some bizarre game where instead of a 6, we have a 7. Okay, for some reason, this game works on the premise that we need a 1, 2, 3, 4, 5, and a 7. So if we roll these twice, we still only have 4 possible outcomes if we're focusing our attention on evens and odds. What's going to change, though, is that each of these outcomes is no longer equally likely to occur because if you notice, there's only 2 even numbers now. and there's 4 odds. So that means that odd is much more likely to turn up than even. So again, even if we're only focused on evens and odds, the sample space is the same. What's different is the probabilities of these outcomes. So because the probability of an even number is now 1 3 out of 3, 2 out of 6 or 1 out of 3, and the probability of an odd number is 4 out of 6 or 2/3. When we multiply these together, like we did before, the probability of getting 2 consecutive evens is 1/9. Even followed by odd is 2/9. Odd followed by even is also 2/9, and 2 consecutive odds is 4/9. So that means they're not all equally likely now, are they? So what about this event F? At most, one even number turns up. Well, nothing's changed. It's still the set containing EO, OE, and OO. But now, based on the chart here, if you add up these probabilities, instead of getting 3/4, you're going to get 8/9. And if you also notice that rule we had before, when we only have equally likely outcomes, this is no longer true. Okay, so in other words, that rule only applies when all the outcomes are equally likely, which happens, but here that's not the case. So instead, the probability of F is obtained by combining the individual probabilities to come up with 8/9. All right, now we're going to introduce sort of a formal background that we need to understand before we go any further. We're going to introduce the so-called axioms of probability. Now, an axiom is essentially a statement that is accepted without proof, and all disciplines are ultimately based on certain axioms, certain things that we take for granted, that we assume are true before we start defining more formal properties. So anyway, here, when you see them, I'm sure you'll realize they make perfect sense. First of all, probabilities are defined so that it's not possible to have a negative probability. So basically what's going to happen here is that a probability of 0 refers to what we're going to call an impossible event. And at the other extreme, a probability of 1 refers to a certain event. That being the case, what this is implying is that all probabilities have to be somewhere between 0 and 1. You can't have negative probabilities, and you can't have probabilities that are greater than 1. Now, when you think about it, there's no reason why the entire science of probability theory has to be based on probabilities from 0 to 1. We could have just as easily chosen 1 to 100 or something like that, but this is how we define probabilities. They must be between 0 and 1. So these are axioms. These axioms essentially tell us that we're going to assume that probabilities cannot fall outside this range. So it's written in a very formal way. First, the probability of any event A is non-negative, meaning that it could be more than 0, but it can't be less than 0. It can be 0 too. The entire sample space, though, has a probability of 1. So if you conduct an experiment, something in that sample space must be true. Okay, so if I roll the die twice, for example, let's go back to the sample space from that last problem. Here it is. If I roll the die twice, something in here has to be true. It's not possible for anything else to happen. So that means no matter how you look at it, the probability of all of these added up must be 1. All right. So if you add up all the outcomes in a sample space, it's going to add up to 1. Now, by the way, the two axioms combined imply that any probability is going to be somewhere in this range. In other words, neither one of them explicitly says this, but the two of them collectively give us this as a result. All probabilities are bounded between 0 and 1. Now, this next one is a little bit more involved. It requires a little bit of explanation. Now, in order to do this, we have to take our minds back to set theory, where remember we introduced the concept of union. So let me just remind you quickly what this is all about. This is a detour into set theory. Suppose you have events A, or sets A and B. So the union of these two is simply a new set that contains all the elements in both. Okay, in other words, I just literally push them together, I tape them together, or whatever you want to call it, into one big new set, which contains all the elements that are in A or B or possibly both. A intersect B is simply all the elements that they have in common. And by the way, there don't have to be any elements in common. If they have nothing, let's say I also introduce set C to be 6, for example. A intersects C. Well, there's nothing in common between A and C, so we have what's called the empty set. There's nothing in there. They have nothing in common. And we say that A and C are mutually exclusive. It simply means they have nothing in common. All right, well, if that's the case, we also, by the way, there's another name for this. There's usually multiple names that mean the same thing in any discipline. This one is no different. By the way, I just want to quickly remind you of a very interesting graphical technique that you've been exposed to, I'm sure of it, somewhere along the way, that helps us visualize these relationships. This is our old friend, the Venn diagram. Yes, the Venn diagram. Yes, you remember this. Perfect for illustrating the relationship between sets. So you've got A and B on the left, they overlap. Here they do not. All right. So, and by the way, in these cases, the box is the entire sample space. All right. So the circles are sets. And so you can see how they're related to each other. And while we're at it, let me show you one more of these. This indicates that B is a subset of A. Okay. And you can see, yes, these are so nice. They help us, you can see just at a glance what's going on here. So anyway, what this next axiom is saying is that imagine you have a series of these outcomes or events that are do not overlap ever. So they're going to write it as generally as possible. So the union, it would be all the shaded areas in here. And what they're telling you is that the probability of this union is equal to the sum of the individual probabilities. I mean, that makes perfect sense. The probability of each one individually, if we add them up, we'll get the total probability of that union. We'll see this again later on, by the way. So this is an assumption that we're making. And so the three axioms form the foundation for all of probability theory. And so nothing we do can violate these axioms. And so everything follows from these three starting points. All right, now, so far we've calculated probabilities for the outcomes of a random experiment. What we're about to see here is the rules that we can use to calculate more complex probabilities, where more than one thing may be happening at a time. So specifically, the rules are the addition rule, the complement rule, and the multiplication rule. Okay, so they are basically explaining to us what to do in the first case, the addition rule. We're trying to calculate the probability of a union of events. The third one, the multiplication rule, refers to intersections between events. And the complement rule, we have to explain that when we get there, what complements actually are. But anyway, let's start with the addition rule. Now, if you notice what's happening here, here's what they're telling us to do. So what I'm going to do is label these regions 1, 2, and 3. Okay, now, why am I doing this? Because I want you to see that A is 1 plus 2. B is 2 plus 3. Now, if I just stop right there, I'm going to add up 1 and 2 plus 2 and 3. And I'm going to accidentally count the 2 region twice. In other words, the intersection here would get counted twice. So what I'm doing here at the end here is subtracting this region 2 in order to avoid double counting. The intersection A intersect B, which is also referred to here as 2. So in other words, that's the reason why we have to subtract this intersection. We're not just adding up the probabilities of A and B, because if they overlap like they do here, that means we'd be double counting their intersection, which is part of region 2. So the logic behind this rule is that we certainly combine both A and B, but we have to subtract off the common area, because if we don't, we'll be counting it twice. Okay. So going back to that die rolling experiment, remember S equals EE, EO, OE, and OO. A will be the event that the first roll is even. Now, this is a set that contains the elements EE and EO, because the first roll is even. B is also a set, exactly one roll is odd, which means you're looking at EO and OE. Both of these are subsets of the sample space, therefore they qualify as events. And we're being asked, what is the probability that the first roll is even or exactly one roll is odd? In other words, what's the probability of A or B? Now, by the way, I forgot to mention this before. This union symbol is sometimes referred to as OR. And in fact, there are books on the market where they don't even use these symbols. They actually write out the English word OR here. because it means the same thing. Logically, it's the same thing. And that being the case, while we're at it, intersect is equivalent to the English word and. And again, some books actually do write the word and here. I guess they figure the symbols are, you have to memorize the symbols, but you know what it means when you see the word and. All right, anyway, so the probability, now this means that we're using the addition rule. So this is a hint. Now, in order to do this though, we need the probabilities A, B, and A intersect B. So the first thing we do is identify what belongs to each of these sets. Remember, we said that for A is the first row is even. This one is at least exactly one row is odd. And the intersection just says, well, listen, do they have anything in common? Yes, they both have an EO. All right. Now, this is a case where all the outcomes are equally likely. So that implies that the probability of A, well, actually, this can be done in two ways. You can either write it like this. Or you could just write because again, they're all equally likely. Okay. And then based on the same logic, B, or okay. And then A intersect B. Well, it's just 1 out of 4, any way you look at it. Okay, so you got everything you need. You just plug these into your addition rule. All right, this is the summary of the results we just got. Here's your addition rule. Remember, this is a half, and this is 1/4. Ultimately, you end up with 3/4 as your probability of getting the first roll even or exactly 1 roll is odd. So imagine you're in the casino playing a game where this outcome means that you win a prize of some kind, you win cash. Then there's a 3/4 chance of winning this cash prize. Oh, wouldn't that be nice? That's a pretty high probability for a casino. Anyway, so now, by the way, it turns out that in order to come up with the same probability, it wasn't absolutely necessary to use the addition rule. Another option we had was to say, well, listen, what sample elements belong in the set? Okay, so if you look at these carefully, I'm just going to copy these two. What I could have done as an alternative is just say, well, you know what? A union B is simply all the elements in these two sets, EE, EO, OE. Oh my God. So then all I had to do was calculate the probabilities of the individual outcomes. Or you could have said, how many elements are there in A union B out of the entire sample space? Because remember, in this experiment, all the outcomes are equally likely. We're allowed to do this too. And you'll get the same answer. So now that raises a good question. Which one should you use? Well, the answer is whichever one is quickest. Now, it turns out that in some cases, you may only be able to do one or the other. You might have a problem where you're given individual probabilities, but you don't know what the sample space is, for example. So you'll either pick the one that's quicker or the one where you have enough information. But it's good to know that you can do it both ways so you can double check your results. All right, now, what about the case when A and B are mutually exclusive? They don't have anything in common. So what's going to happen is their intersection is empty. That means this can't happen. A and B do not have anything in common. The probability of A and B both being true is therefore equal to 0. All right, so when they are mutually exclusive like this, the probability of their intersection is 0. In other words, it's not possible. Just as a quick example, suppose that I'm picking a number and A is the event that it's odd and B is the event that it's even. No number can be both, so the intersection between these two is the empty set. And it's therefore not possible for me to pick a number which is both even and odd. So what does that say about our addition rule? Oh, well, look what it does. Oh, so when A and B are mutually exclusive, the probability of them both being true is 0. So that means I can drop that out of this expression and I end up with the so-called simplified addition rule. And that would be illustrated on a Venn diagram like this. Here's your A, here's your B. And the union between the two would be obtained by simply combining these. Oh, that's nice. And of course, if you use the general rule, it wouldn't really matter because you'd just be subtracting 0 at the end anyway. All right, so let's take a look at an example of this. Using the same sample space we had before, the die rolling experiment, let's let A be the event that the first roll is even. And then we have OE and OO for the second one. The first roll is odd. Now you can see they have nothing in common, do they? That, of course, indicates that this probability is 0. It's not possible for A and B to both be true. Okay, it's not going to happen. So therefore, on the other hand, we could still calculate the probability of A or B. Well, you know what? That's very simple. A is a half, B is a half, and therefore we end up with 1. So this tells me that A or B must be true. But they can't both be true. All right. So now we understand the addition rule. Let's take a look at the second rule, which is the complement rule. Now, first we have to define what do we mean by complements. Now, normally in English, the word complement means that two things are somehow related to each other. If you took a course in economics, you might recall that two goods are said to be complements if they're consumed at the same time, like peanut butter and jelly, or spaghetti and meatballs, or something like that. Well, here, it means something a little bit different, but the two are very closely related to each other in an important way. In order for A and B to be complements, we have two conditions that must be met. First of all, their union gives us the entire sample space. And secondly, their intersection is empty. Right? If both of these things are true, A and B are complements. Now, that's a very abstract definition. Let's think of some real-world examples. Okay, let me sneak a few in here. So yeah, these are the two conditions that must be true. Uh-oh. Yes, I broke, actually, I just realized to my horror, for a second, it seemed to be freezing up, and I realized I haven't saved this in a while. And that was a very foolish move. You know how computers are. You don't save your work very, very frequently. You're just asking to lose it all. All right. Oh, I hate to say it, but I think this computer is on its last legs. I think it's time to get a new one. But anyway, those are the two conditions. So what would be a good example of complements? All right. So how about this one? An experiment consists of choosing a card from a deck. A will be the event that the card is read. B will be the event that the card is black. All right, now in this example, the sample space is the deck. I'm not going to write down all the individual cards, of course, but which we could write as I don't know, something like this. Like I'm not going to write out all the individual ones. That would be a huge waste of time. But so the question is whether A and B are complements. Well, okay. What is the union of these two? The union of the red and black cards is the entire sample space, the entire deck, that is. So that condition is true. What about the second condition? So then that becomes, are the red cards and black cards mutually exclusive? Yes, no card can be both. So therefore, both conditions are met. A and B are complements. Oh, it wasn't that painful. Red and black cards. So there's other possibilities too. For example, if we define sample space to be natural numbers, and A equals the odd numbers, and B is the even numbers. A and B complements. Well, is the union of A and B equal to natural numbers? Yes. Okay, in other words, every single one of those numbers is either even or odd. We don't have anything else to choose from. And secondly, do they overlap? Or, well, I guess what we should say is, are they mutually exclusive? Yes, because no number can be both even and odd. Or at least no number in the natural numbers. Supposedly, some mathematicians think that 0 should be considered both, but that's not in this set. So therefore, A and B are considered to be complements. So you get the idea now. You should be able to identify complements whenever you run into it. Like, imagine you go to a coffee shop and you think of A being the regular coffees and B being the decaf coffees. Well, there's another case where you have two complements because all the coffees have to be one or the other, but they can't be both. All right, anyway. So by the way, notation wise, we're going to use this little C to indicate a complement. Whatever A is, its complement will be defined as AC. Well, if that's the case, based on what we just discussed, we can write this complement rule in two equivalent ways. The bottom line here is that since both events must be true, one of them must be true, these two add up to 1. And by the way, if you notice, this equals 0, so we don't need to worry about it. We just add these two up, and we end up with A plus probably AC equals 1. And we're using the simplified addition rule because A and A complement by definition are mutually exclusive. So if you rearrange this statement algebraically, you'll get these two. And that's our complement rule. So it's really straightforward, very straightforward, as a matter of fact. So let's take a, once this thing is finished saving, we can go ahead and, yeah, here we go. So back to the die rolling experiment. Let's define the second roll, A being the second roll is even. And the second roll is odd. So what do you think? Are they complements or not? Their union is OE, EE, OO, and EO, which even though it's not written in the same order, this matches up with the sample space. And their intersection is empty. So the answer is yes, they are complements, which implies that the sum equals 1. So these are all true as a result, as a consequence. Therefore, and we're just going to demonstrate that by writing out the actual probabilities. because the outcomes are equally likely, you can see that A and B both have the same probability of 1/2. And so, yeah, they're complements. Now, for some problems, you might find that it's easier to use the complement rule rather than calculating a probability directly. So again, it's important to understand the different ways this rule can be used. All right, and we'll get back to some examples of this. Actually, let's make one up right now. Suppose a card is chosen from the deck. A equals event that it's a royal card. You know what? This is something I've always wondered about. I'm going to go look this up right now. I've always wondered if there's a name for the non-royal cards. Oh, it says here they're number cards or pip cards because the royal cards are also known as face cards because those are the only ones that have actual face people drawn on them. Um, oh, okay. I guess that would make sense. The number cards. Huh. Sometimes they're called spot cards. How do you like that? Well, now I know. So here's the part I want to know. What is the probability be? Now, we can certainly write out all the spot cards. But let's try this approach. There are 12 royal cards in a deck of 52 cards. It's the king, queen, and jack of each of the 4 suits. This means that the probability of drawing of A, and they're all equally likely, must be 12 out of 52. A and B are complements because all cards must be either a royal card or a spot card, and no card can be both. That being the case, B is the complement of A. So that's A complement. And this is a superscript. Making superscripts in the PowerPoint is a little bit awkward. And that's it. You see, in this case, you notice what I was able to do. I was able to avoid counting all the spot cards by noting that the royal cards, there's 12 of them, which implies the remaining 40 must be spot cards. And therefore, my probability is simply 40 out of 52. So I may have saved myself a little time with that, especially if there's a large sample space. Sometimes this approach can be very, very useful. Okay. So anyway, now the multiplication rule. The third and final rule that we're going to look at is the multiplication rule. This one involves intersections. In other words, we're trying to find out the probability that two different things are both true. Now, unfortunately, this rule is very, very complicated. So we're going to need to take a step back and introduce some new concepts before we dive into this. We have to introduce three new types of probabilities before we can continue. So I've got an example here, which you'll find interesting because it involves students in a business school. We're going to use a so-called joint probability table, which illustrates data broken up into two categories. And we're going to have on that same table what are called joint probabilities and either marginal or unconditional probabilities. So we're going to use this example. To come up with the results that we need before we introduce the multiplication rule. Okay, so let's look at the table. Now, this is some unnamed business school, which happens to have exactly 500 students. And the school offers bachelor's degrees and MBAs or master's degrees in business. So BBA stands for Bachelor of Business Administration. MBA stands for Master of Business Administration, which is what comes after college if you're interested. Then we're going to assume that this school offers three majors: finance, accounting, and marketing. You can see the distribution of the students by the table. For example, there's 175 finance majors, 215 accounting majors, 110 marketing majors, 400 bachelor's students, and 100 master's students. Now, these are the interesting ones because I can see, for example, here that 130 students are getting their bachelor's degree in finance. 35 students are getting their master's degree in accounting. So these probabilities in the center of the table have a special name because here two different things are both true at the same time. In this little part of the table, these are known as joint probabilities. Okay. For example, the probability of somebody getting a bachelor's degree in finance can be written as the probability B intersect F. Remember, this is the equivalent of and that would be 130 out of 500. And then we also have this MBA in accounting. And we can make it like that. Actually, I mean, if you want, you can calculate this out. This is 26 and this is 7. So altogether, we have 6 joint probabilities in this table. Okay. By the way, I do want to point out that we're going to use letters to represent these outcomes. There's just one awkward thing that happened in this table. There's 2 M's, there's MBA and there's marketing. So we're going to randomly call this one T. And with that in place, we can calculate any probability we need. What about these down here, the totals? For example, this one refers to all the finance majors. And that will be 175 out of 500. 35%. So the probability of a single event has its own special name, which I don't have room for here, so I'll write it on the next slide. This is called either a marginal or unconditional probability. So you can see there's several of these as well. We've got the probability of F, A, T, B, and M. There's 5 unconditional or marginal probabilities, and there's 6 joint probabilities, which tell us the probability of 2 things both being true. All right. So now, and by the way, I went ahead and filled them in all for you, so you can go through, for example, probability of getting a master's degree in marketing would be this 20 out of 500. So you can go back and double check them all. And as we started to say, the marginal probability is either a row total or a column total. Only one thing is true. For example, here, the probability of B, just B, is 400 out of 500. Probability of M is 100 out of 500. Probability of F, which we've already done, of A, and then T, 110 out of 500, which is 22%. Those are the unconditional or marginal probabilities. Now, with all that being said, the third and final type of probability that we want to introduce here is basically derived from these. Okay. So this new probability. Oh, by the way, what I did here is I showed this new version of the table by going through the entire table and dividing out all the entries by 500. The raw totals, which you're seeing here, have been converted into probabilities. Both of these tables are equivalent to each other. I think that you'll find as you go along, though, this version is easier to work with, unless you need to know the individual raw totals. If you're only interested in probabilities, then you're probably better off with this table than this one. It just saves you a little work. Now, if you're the administrator at the school, it may be important that you need to know, oh, there's 180 students getting a bachelor's degree in accounting. But if you're just trying to calculate what proportion of the students are studying, getting a bachelor's degree in accounting, this might be good enough, 36%. All right, so the trickiest one is right here, the so-called conditional probability. This is what we need for our multiplication rule. Now, it's called this because what's happening is that we're going to be asked to calculate the probability of one event based on the knowledge that another event is true. So that hasn't happened up to this point. In other words, imagine being told, or let's just say you want to know the probability of being late to school tomorrow. Well, a conditional probability for that case could be, what's the probability of being late for school given that it's supposed to rain? That extra piece of information will have an influence on whether or not you're late for school. And that would become a joint probability. The probability that you're going to be late without any other information would be the so-called unconditional probability. But the probability that you're going to be late, given that it's supposed to rain, would be considered a conditional probability. So we have to have a formal way of calculating these because, as I said, the multiplication rule, which I'm saving for last, is defined in terms of conditional probabilities. All right, so I think because this is fairly involved, I think this is a good time to stop right here and we can pick this up next time. We'll introduce the formal definition for conditional probabilities and we'll go back to our table and we'll calculate some conditional probabilities. Then we'll introduce at long last the multiplication rule. Okay, so that's something for you to look forward to next time, and I'll see you then.